Good afternoon, good evening, everyone. This is Mr. Johnson, AP Chemistry. We are now beginning Chapter 15, and Chapter 15 deals with, as you can see, a little chemical equilibrium. As we go throughout this chapter, we'll certainly be talking about different types of chemical equilibrium, how it affects reactions, and things like that. Let's go ahead and move on to the next slide here. So today what we're going to be talking about, we're talking about what dynamic equilibrium is. We're going to talk about writing equilibrium expressions, and then we're going to understand what what equilibrium is and what the value of that KEQ symbol is. So as we know, when reactions occur, many times they go forward. And as they go forward, they start to produce products. And then those products pretty much just stay there. A lot of times what happens though when you have an equilibrium reaction is the reaction is proceeding forward, and as it starts to proceed forward, it also happens to be going, and once you start producing some of the products, it also starts to react in the opposite direction as well. Oh, so when you have what's called chemical equilibrium, you've got two reactions going, one going forward and then one going backwards. And what's important about that is that they're occurring at the same rate. So as we talked about in kinetics in chapter 14, as things continue to progress forwards at a certain speed or rate, thinking about rate laws and things like that, you've also got a reaction proceeding backwards at that same rate. And just like throughout all this school year, we've talked about different constants. The gas constant, we've got the boiling point and freezing point constants, we've got rate constants, we've got all these constants. When you deal with equilibrium, you also have a constant. And this is also a constant that does not, that certainly does, excuse me, it does change. So like with gases, the R, the gas constant was always 0.0821. With equilibrium, it is not always the same value. Sorry about that there, kiddos. My wife walked into the room, and this is the first time using this, so I don't really know what I'm doing, so get used to it. Anyway, I can't remember what we were talking about. It's just like in class, right? See, it's all good. Anyway, so the general form of the equation that we use for equilibrium is we use the capital letter K. Notice the difference here. Here we've got the small letter K. That is used for rate constants. You've got KF and KB. Those are used for solutions. And our general form for the equilibrium constant is KEQ, where obviously the EQ stands for equilibrium and the K just stands for constant. Now, let's say we have how do we find what that K value is? Let's say we have a reaction here where A is going to react with B and it's going to make C and D. One thing, first of all, notice that double arrow there. The double arrow means the reaction is also not only proceeding forward, it's also proceeding backwards. Like we said, they are occurring at the same rate. So we know that really, like if we go back to that very first slide, in our what it looks like to us is nothing's really happening. As we start out, we start with the N2O4. It slowly becomes NO2, but the NO2, as you can see, this one here and this one here will hit each other, and then they'll go back to being N2O4. So to our eyes, when we look at a reaction that's in equilibrium, we see that it appears as if nothing's changing. But something is changing in that the forward reaction is still occurring, the reverse reaction is still occurring, and just to us it looks like nothing is happening. Okay, so coming back here to this reaction where A reacts with B to make C and D, but also at the same time C is reacting with D to go backwards to make A and B. The equilibrium constant expression for this can be written a couple of different ways. And I'll talk about this one here on the left first. Notice that instead of saying KEQ, it says KP. When you use KP, it means the same thing as KEQ. It's just being a little bit more specific in that the P stands for pressure. So this is the equilibrium constant using the pressure, and certainly you would use pressure if you were dealing with gases or something like that. So notice here, so the equilibrium constant using pressure is equal to the pressure of gas C in this case times the pressure of gas D. Notice that the products are on top, the reactants are on the bottom. It is always like that. Whenever you write an equilibrium constant expression, the products are on top and the reactants are on the bottom. And and you can also see that the coefficients from the balanced equation, for example, if this was 3C's plus 4D's, that this number here would be a 3, this number here would, or this letter here would be a 4. So you'd have the pressure of C raised to the third power, the pressure of D raised to the fourth power. Okay, same thing with the reactants. So this is a little bit different from rate laws, in that rate laws, remember that we only used reactants. So if this were a rate law, we would say the rate is equal to K times the concentration of A times the concentration of B. Sorry about that. But with equilibrium, notice that our products are on the top, our reactants are on the bottom, and the coefficients in the balanced equation are used as the powers in these. Well, how is this here different? How is Kc different from Kp? Remember, the P stands for pressures, the C stands for concentration. So notice here the P, all of these are pressures. Here you've got the square brackets like we use with rate laws where you've got concentrations. Notice it's the same thing though. It's the products over the reactants, and it's always products over reactants, where the coefficients from the balanced equation are used as the powers in that equilibrium. Okay, so the P is for partial pressures of each gas, and then the square brackets, as we know, is the molarity of each of the species found in that solution. Okay, here's an example of a very common process, a very famous process called the Haber process, where, as you can see, nitrogen gas and hydrogen gas react with each other, and they do produce ammonia. And remember, this is not just a one-step process. This is just the overall reaction. So remember when we talked about reaction mechanisms we don't really look at with equilibrium. We just look at the overall equation. And so when we're doing this, that asks us to write the equilibrium expression for this reaction. So right away we can see they're all gases. So we could do it, if we come back here to this, we could do it as Kp, and we could also do it as, we could do it as Kc theoretically. Usually on the AP exam they will specify either Kp or Kc, but if you just put K, that is certainly fine as well. So if you would, right there on your notes, right below this, if you would write that, what you would think that reaction would be, and then you can take a look at it here in just a second. Okay, if you're not quite sure, then just kind of follow along here. Again, we've got our products. Our products are NH3, and because it's a gas, we're going to do it as Kp. As we do it as Kp, we're going to have our products over our reactants. So we're going to have NH3 on top, and we're going to have nitrogen and hydrogen both on the bottom. Now in the case of nitrogen, you're not going to have anything raised to the power because it's just 1. But ammonia on top, you're going to have it raised to the power of 2, and then hydrogen is going to be raised to the power of 3. So this is our equilibrium expression for this reaction. And now if they were to, for example, tell us what the equilibrium values of ammonia, nitrogen, and hydrogen were, then we could put those numbers into the equation, and we could actually solve for the value of Kp. Okay, hold on here for just a second. All right, sorry about that. Now, as we're doing this, if you're having problems understanding what I'm talking about, you can certainly rewind the video. If you still don't have any idea what's going on, then please write questions down, and then in class the following day we can certainly talk about it. So if we look, here's another example. This is actually the reaction from the very beginning of the slideshow, where you've got N2O4 decomposing into two NO2 molecules and then also going backwards. So if they were to ask us what's the equilibrium expression for this reaction, we should be able to look at that and go, okay, we've got our product is NO2 and there's two of them, so it's going to be K is equal to the pressure of NO2, and that's going to be squared because, again, there's two of them. And then we've also got N2O4 is our only reactant, so that goes on the bottom, not raised to any power at all. Sorry, I guess one of the problems of doing this is you have children at home and they keep walking in, so get over it. You'll be all right. Okay, so anyway, back to this. So now if they were to actually give us the pressures of NO2 and the pressures of N2O4, we can just put those numbers into the equation. So we'd put 0.0429 up here where our NO2 is. We would square it, and then we would divide, or excuse me, I said that backwards, didn't I? The 0.526 would go up here, and we would square that, and then we would divide by 0.0429, and then we would get our answer of 6.45. A couple things are important. Remember, with rate law constants, one of the important things about rate law constants is being able to determine the units on those rate law constants. With equilibrium, the units can vary so much they just said, you know what, forget about units. There's no units. So whenever you have an equilibrium value as your answer, it's just a number. And we'll talk about what that number means here in just a little bit. Okay, here's a couple things as well. Notice that here's 4 different experiments. In each experiment, they start with different amounts of N2O4 and NO2, and they basically just put them together. But overall, you can see that the equilibrium value does not change. So what that means is it doesn't matter with how much you start with. In both cases, it's different. But the value of KEQ for a reaction always remains the same. Unless you change the temperature or something else, something like that. Okay, so the equilibrium constant expression only depends on the stoichiometry. Okay, only depends on the fact that there's a 2 there and that's squared. And once those values reach equilibrium, the ratios are always the same. And so you end up getting the same value for KEQ. Okay, so here's 3 different reactions. If you would, go ahead and pause this video. And try to write the 3 equations, the 3 equilibrium expressions for this right there on your notes, and then we'll look over each one of them. So please pause now and do it, or not, Bryson, whatever, just go ahead and just listen to me, that's cool. Anyway, so if we look at these, for letter A, we've got oxygen as a product, and there's 3 of them, so we've got the pressure of O2 cubed. We've got ozone as our reactant. There's 2 of them, so that's going to be squared. For letter B, notice that in both cases we've got gases, so in both cases I wrote them as KP. Now if this were an exam, would you have to write KP or KC? You can just write the letter K. The little letter that comes after it is not that important. What's important is this information over here. So for letter B, we've got NOCl as our product, and there's 2 of them, so we have the pressure of NOCl squared over the pressure of NO squared times the pressure of Cl2, and again, that's just the regular old pressure of Cl2. And then for our third one, here we do have an aqueous solution, so notice that I use Kc and not Kp. Our product is AgNH32+, so that's on top. There's only 1 of them, so there's nothing raised to the power. You've got Ag+, and then you've got NH3, and again, notice the 2, and that's squared. So what you should remember from this is that it's always products over reactants, and that the coefficients from the balanced equation are the ones that you use, or the ones that go up in the corner as powers on these equations. Now, how about Kp versus Kc? Are they the same thing? Well, certainly not. One of them uses pressures, one of them uses concentrations. So numerically, they are different, which is why it is important to specify which one you are going to use when you're actually doing the math involved with it. Okay, and this is an equation that is given on the AP exam. You definitely do need to be able to convert between one or the other. If you know Kc and you need to find Kp, you take Kc times R, which again is the gas constant, 0.0821. T is the temperature in Kelvin, and then delta N is the only really part you have to think about. And delta N, as you can see here, is the moles of the gas product minus the moles of the gas reactant. So if we come back, let's look at an example here. Notice here that we've got 3 moles of gas product. We've got 2 moles of gas reactant. So if we bring that back to here, we would take our Kc value, times it by R, times it by T, and then we take the product, which was 3, minus the 2. So our change in N for that reaction would just be equal to 1. Okay, if we look at the second equation, here we've got 2 moles of gas product. Here we've got 3 moles of gas reactant. So in that case, our delta N would be 2 minus 3, so that would actually be a negative 1. So it would be raised to the negative 1 power. Okay, and really it's with gases where they might ask you to differentiate between one or the other, because with gases they can give you moles and they can give you volume. Well, if they give you moles and volume, you can get Kc. But they can also give you pressures where you can find Kp as well. So with solutions, I've never seen them talk about Kp, because obviously you're dissolved in water, and pressure isn't what you're using concentration. So you do these equilibrium problems, you get an answer, and those numbers should tell you something. Okay, they can be really, really big numbers. Sometimes they're really, really small numbers, but they do definitely provide us with information about what's in that equilibrium mixture. If you get a number that's very big, and by very big we just mean bigger than 1. If you get a number bigger than 1, let's look at what that might mean. If the number is bigger than 1, let's look at A. If Kp is bigger than 1, that means that this number has to be bigger than that number. Which means if the top number is bigger than the bottom number, and the top number represents the products, that means that all that means that you have more products than you do reactants. So when K is bigger than 1, we say that the reaction lies to the right, which means that basically in that equilibrium mixture, when you have equilibrium, that does not mean that you have 50% reactants and 50% products. It just means that the forward reaction and the reverse reaction are happening at the same rate. So it tells you nothing about the fact that it's equilibrium tells you nothing about how much product or how much reactant you have. That's what K tells you. K tells you whether you have more product or whether you have more reactant. And the way that they say it is they say it lies to the right, meaning you have more product, or it lies to the left, meaning you have more reactant. Okay? So if K is greater than 1, then the equilibrium lies to the right and you have mostly products. If the equilibrium constant is less than 1, that means it lies to the left and you have mostly reactants. So here we can see that as well. If Kq is greater than 1, you've got mostly products, very few reactants, and then vice versa down here on the bottom. Okay. Now let's talk a little bit about the direction of the chemical equation and what that means to KQ. When we talked about enthalpy changes way back in chapter 5, if we have the enthalpy change for this reaction right here, N2O4 becoming 2 NO2s, and we were to flip that equation around like here, we would just flip the enthalpy change. So if the enthalpy change for this first reaction was positive 25 kilojoules per mole, for the reverse reaction it would be negative 25 kilojoules per mole. With equilibrium constant, though, as you can see, that does not happen. The KEQ for this reaction is not a negative 6.46. There's actually, you never ever will have a negative value for KEQ. KEQ is always a positive value. It's either going to just be greater than 1 or less than 1, but you can never have a negative pressure or a negative concentration, so you'll never have a negative KEQ. Notice though that the KEQ is very different for the second equation than it is for the first. Why are they so different? This is an important rule to understand, that the equilibrium constant expression for a reaction written in one direction is the reciprocal of the one for the reaction written in the reverse direction. So this number right here, if you take your calculator out and you take 1 over 6.46, it's equal to 0.155. And so when you flip an equation around, what happens is the KEQ becomes the reciprocal, or 1 over the original value of KEQ. So for this reaction, as we know, KEQ is greater than 1. The reaction lies to the right, so you've got more NO2 than you do N2O4. Well, this is the same reaction. Notice that NO2 in this case is a reactant though, and notice our value for KEQ is less than 1. So again, no matter how you look at it, there's more NO2 in this reaction and in this reaction. In the first reaction, it lies to the right. In the second reaction, it lies to the left. Okay, so just like how we just saw, you can manipulate chemical equations, and that will affect the value of KEQ. Just like how we just saw, if you flip an equation around, it is the reciprocal of that equation. The second one is if you take a reaction and you multiply it by a number. So this is kind of going back to Hess's law, where you can combine different reactions to make a new reaction, and you can make a new value for KEQ. In this case, if you multiply an equation by a certain number, you don't multiply the value of the equilibrium constant, you actually raise it to that power. So let's say you have to triple a reaction, you're gonna take the equilibrium constant raised to the third power. Okay. And then this third step just says that if you add them all together, it is the product of the equilibrium constant. So this is very different from Hess's law, in that in Hess's law, when you flipped a reaction around, you also just flip the sign of the value of the enthalpy change. If you on the second one, if you multiply an equation by a number, you just multiplied the enthalpy change. And on the third one, you just added the enthalpy changes up. Notice that every single one of those rules is different. In this case, you multiply the KEQs. You do not add them together. Okay, so here's a reaction where the first KEQ is 0.42, the second KEQ is 7.2. You put those two equations. Notice that Br2 would be an intermediate in this reaction, so Br2 is not in the overall reaction. We do not need to change anything in these reactions to make this reaction. But when we put them together to get KEQ, we multiply this value times that value, and we get our value of KEQ as 3.0. 3.0, remember, that's greater than 1, so that's telling us that we do have more product than we do reactant in this equation. Okay, so here's another reaction where you've got HF decomposing into H and F minus. Then you've got the H2C2O4 also decomposing. We've got two different values for KEQ because they're two different reactions, and they want us to determine the value of the equilibrium constant for that reaction. Okay, so a couple things. First off, right away I'm looking here, I see two HFs. The only place up here where I see an HF is right here. I'm going to have to double this reaction. When I double that reaction, what am I going to have to do to KEQ? Do I double KEQ? No, I do not. I raise it to the power of 2. So we see our 6.8 times 10 to the minus 4th. That is now squared. Okay, so I didn't times it by 2. I times the equation by 2, but the value of KEQ is squared. Okay, and then my next reactant is C2O42 minus. Notice up here that it is a product. So I need to flip that second equation around. And when I do that, when I flip an equation around to make these the reactants, these the products, I also have to flip KEQ. So I'm putting 1 over 3.8 times 10 to the minus 6th. Okay, and then I'm going to put the two equations together. So I don't add them, I multiply them. And so my overall equation becomes this. And then my value for KEQ is equal to 0.12. Okay. Take out your calculator, check the math on that, make sure that is a correct answer. I may purposely on these put a wrong answer and see if you're actually paying attention or not. And in this case, I got an answer of 0.12. Okay, and then really just a final thing, the comment about equilibrium constants is when we're talking about pressures of gases or we're talking about concentrations of solutions, a lot of times what we have when we have we will have different substances in the different phases. Okay, for example, here, if you put lead chloride in water, it is an equilibrium where it does slightly dissociate. But if we talk about the concentration of PbCl2, you can't really talk about the equilibrium. Excuse me, you can't talk about the concentration of PbCl2 because it's solid PbCl2. It doesn't really have a concentration associated with it. There certainly is a concentration of Pb2 plus, certainly a concentration of Cl minus, but PbCl2 doesn't have a concentration associated with it because it is just a solid compound. Okay, so when you write equilibrium equations, you always use gases, you always use concentrations for things that are dissolved. But number two, highlight or underline or do something with this to make you remember this. If you have a solid or a liquid, you do not include them in the equilibrium constant expression. Okay, well, what do you do with them? You just leave them out. This is right here. This is the correct equilibrium equation for that reaction. A lot of times with acids and bases reactions where you've got an acid reacting with a base to produce water, water is a pure liquid. You do not include water in equilibrium expressions. You only use things that are aqueous or things that are gases. Okay, so PbCl2 has been omitted since it's a solid. Okay, and I still remember every year question number 1 is on equilibrium. And a lot of times that very first letter A in question number 1 is something to the effect of write the equilibrium expression for the reaction. And I still have students every year put the solids and put the liquids into the equation. Please, please listen to me. Do not put, if it says S, solid, do not include it in the equation. If it's water, usually it's only water, but if it is a liquid, you do not include it in the equation. Okay, so we talked a little bit about what equilibrium is. We talked about what the constant is, what Kc and Kp are, and if you have a large value for Kq and what a small value for Kq, what those things mean. Okay, and please, again, the solids and liquids, please do not include those in your equations. Okay, hopefully this worked well for you. Hopefully you took some notes there on the notes that I left for you. Please bring those to class tomorrow. We will look over them and then we'll take these review questions here and start going over them.